Like, what I
Okay, I'm not going to go over the whole test, but I did have a request to look at the last, this sequence one right here. So I will at least give you, okay, some ideas about this one. So I think everybody pretty much figured out the next two terms of the sequence that were 63 and 127. Okay. And then there were two classes of people. Okay, so some people wrote, okay, of course, your recurrence relation always has that, that the first term should be 1. Like that should be a constant for everybody. But the recursive rule of how you found the nth term was a little bit different depending on who you were. So some people looked at and said, okay, well, if I take the previous term and double it, okay, so if I double 1, I get 2, add 1, I get 3. If I double 3, I get 6, add 1, I get 7. If I double 7, add 1, I get 15. If I double 15, add 1, I get 31, and saw that pattern. So some people were of the, I'm going to double the previous term and then add 1. Okay, so that is a perfectly acceptable, fine recurrence relation. Other people looked at this and said, oh, I added 2, then I added 4, then I added 8, then I added 16, and they noticed that they were adding powers of 2. And so other people, just because of the way that you look at things, said, okay, I'm going to take the previous term and I'm going to add the power of 2 on there. Let me find... So both of those are completely acceptable recurrence relations. It doesn't matter which one you use. Okay, either one of them, if you do the proof, you will get this to be an explicit formula that matches them. Okay, so it doesn't so as long as you come up with a legit recurrence relation, it will match the closed form. Okay, and so, for both of these, the base case is the same. Okay. So the base case for both of these would be n equals 0. That's the first non-negative integer is 0, right? Okay, so we know from both of the recurrence relations that a sub 0 is 1. Okay, so regardless of 1. Now this, and then if we look at this, then 2 to the 0 plus 1 minus 1, that's 2 to the first, which is 2 minus 1 is 1, right? So that's, both of those have the same base case. Okay. But then they'll differ in the inductive case, or in the inductive step. So here, the inductive step, I would assume that, okay, well, so that for both of them, I'm going to have the kth term is 2 to the k plus 1 minus 1. Okay, I assume that. Okay, the assumption is the same. Okay. But then how you find the k plus first term is going to be, and we want to prove that the k plus first term is 2 to the k plus 2 minus 1. Okay, that's the same. Okay, but depending on whether you use this recurrence or this recurrence relation, you're going to get slightly different here. So let's go with this side. If you were of the school that, oh, I doubled it and added 1, then you would say, okay, well, to find a sub k plus 1, I know the definition from my recurrence relation is I'm going to go 2 times the previous term, the one that comes before k plus 1 is k, and then I add 1 to that. Okay. And then I go, oh, well, that's 2. Well, I know a sub k is this from my inductive hypothesis, so I'm going to put 2 to k plus 1 minus 1, okay, in parentheses, and then plus 1. Okay, so notice all I've done is substituted the 2 to the k plus 1 minus 1, that in for a sub k, because those are equivalent. Okay. So when I distribute my 2, I'm going to get 2 to the k plus 2 minus 2 plus 1, which is 2 to the k plus 2 minus 1. which is exactly what I was hoping to prove. Okay. So that's, that's the quick, obviously you want to put some other words in there, by the inductive hypothesis, etc. But that's the general outline of how you're going to do it. This one, on the other hand, okay, I'm going to say, okay, to find the k plus term, I'm using this one instead. So I go to the previous term, which is a sub k, and then I add 2 to the n. Okay, well, I go to my inductive hypothesis, and again, I substitute, well, a sub k is really 2 to the k plus 1. Okay. Oh, this should have been k plus 1, because that's the nth. Minus 1, and then I take that and I add on to k plus 1. Okay. Well, 2 to the k plus 1 plus 2 to the k plus 1, that's 2 times 2 to the k plus 1 minus 1. So this is 2 to the k plus 2 minus 1. Okay. So they both work. They both equal 2 to the k plus 1 minus 1. It's just, in your proof, you'll use this definition if you chose this recurrence relation. You'll use this definition if you chose this recurrence relation. Oops. And it was about, I don't know, almost 50-50. Maybe a few more people did this one than that one. But there were, it wasn't like everyone chose one or the other. I saw lots of these and lots of these. And I saw lots of nothing as well. But, yeah. But as far as the ones that were correct, I saw both. And some people that maybe just ran out of time. Okay. Any other major questions? Yes? Yes, we can do the bonus question. Oh, I hate that my pen bleeds through. Okay, so that's the bad thing about, they show up really nicely, but then they bleed through. Do I have another? I might just have to do it on a separate page. Okay, so for the first one, we know that if you want to find the summation, we see this as an arithmetic sequence because you're adding 4. Okay, definitely an arithmetic sequence. So those of you that saw that, you said, okay, well, I know if I take the first term and I add the 26th term and divide that by 2, so the average of the first term and the 26th term, and then I multiply that by how many terms there are, I should get the sum. So if you remember that formula, it's the average of the first and last term in the sequence times 26. Okay. So the first term is easy. It's right there. This is a sub 1. Okay, is negative 17. Okay. The trick on this one is just figuring out what the 26th term is. To figure out the 26th term, we say, okay, well, the 26th term, I know I'm going to start with the first term, which is negative 17, and I'm going to add on 4 and 4 and 4. And how many times do I have to do that? I have to do that 25 times. Okay, so I have to add on 25 common differences to get to the 26th term. So that's going to give me 100 minus 17, or 83. So you'd put that in there. Okay, I think I have it worked out. Let me find the answer. Does somebody have that one? If you have it, yell it out. I'll have to find the line. What is it? 858? Okay. Maybe? Yes? No? Okay. So anyways, put it in your calculator. I've lost mine. My pages are out of order. Oh, here. Yeah, 858. Yep, that's the right. Okay. All right, so that's the first one. And then the second one, you may have noticed that this is a geometric sequence. So the summation is a geometric series the value that we're multiplying by every time is -2. So if I take -3, multiply it by -2, I get 6. Multiply by -2, I get -12. Multiply -2, I get 24. Okay. The geometric one is easier. Okay, so if you want to find the series, you know it's the first term. Okay, and then it's times the r to the n minus 1 over r minus 1. Okay, where r is your common ratio, and n is the number of terms. So in this one, we had 14 terms, and our first number was -3. So that's going to be -3 times, and the big problem that people did here is they wrote like -2 to the 14th minus 1 over -2 minus 1. Okay. So, and then some people got the wrong sign or just slightly off on this one, because is -2 to the 14th equal to -2 to the 14th? Are those the same thing? No, those aren't the same thing. And what should I have put here? -2 to the 14th or -2 in parentheses to the 14th? I should have used the parentheses, right? Okay. So when I take a negative number and raise it to an even power, I get a positive number, right? If I don't put the parentheses there, it's going to do the 2 to the 14th first, and then it's going to negate that. And so it's going to be slightly off. Okay. So if you were one of those people that had the formula right and forgot your parentheses, I gave you half of the bonus points, just because at least you knew the formula. But you only got full bonus points if you put your parentheses in. Okay, and I think, let me see, that one turns out to be 16,383. Okay, so that was the bonus. Anything else? Okay. Hopefully you can look at my comments. If you have any questions, shoot me an email or come see me in my office hours. Whenever, Okay. So, our goal, we have such a short amount of time left. So, chapter 5 is on functions. Most of what you see in chapter 5 should be review of stuff that you've seen in your lifetime in the past. So we are going to kind of fly through chapter 5. You know, stop me if I'm going too fast, but we really need to get through chapter 5 so that I'm not tempted to fly through chapter 6, because that's where a lot of the new stuff and more difficult concepts are. So, we're going to, get through this week so that we have time to spend on chapter 6. Okay, and then I hope we'll see if we can, I would like to touch on at least the normal forms from chapter 7, just because I know if you are going into AI classes that you're going to have to know what, like, some of the various disjunctive and conjunctive normal forms are. So I'd like to at least go over those from that chapter. Yes? Probably not a quiz next week. Okay, because next week is Thanksgiving week, and I'm actually not planning to be here on Tuesday, so we're not going to meet for class, but we really have to get through material. So I'm going to record and post a lecture for you to watch, okay, and which you can watch at your leisure or whatever, like eat your turkey, sit down, whatever you need to do. But so yeah, so one of my teacher friends invited me to her birthday celebration, and just going to this candle making thing, and it's on Tuesday, and I really want to go, and you guys don't want to come here anyways on Tuesday, so I'm just like, all right, I'm just going to record a lecture, put it up there, but we really need to get through some of the material, because we really need to get the relation stuff, that whole chapter done. Okay, so we can't really afford to completely take it off, but we'll just do it somewhere else. All right. So with that, we will start chapter 5 and talk about functions. Okay. So you probably have at multiple times, when you were in high school, when you were in calculus, all sorts of classes, talked about what a function is. Okay, there's the classic picture that you have where you have the little black box that's a function, and you have a value coming in like x, and you have a value coming out. And then you maybe call that y, or you maybe call that f of x, and you have this kind of picture of what a function does. It takes an input, it does something to it, and it produces an output. Okay. Plus you're computer programmers, and you know what functions do. They take input, they do something, and they produce output. Okay, so a function maps elements of a set x. So if you think about where the inputs are coming from, there's this big set of elements here. I call that set x. So this, like lowercase x, I get that input out of this big set of a collection of things. Okay. And I put it into my function, and it produces a value. And the value that produces, okay, is when I collect all the different values that could be produced, I maybe would put those in a set capital Y. Okay. So if you look at the formal definition, a function maps an element of sets x, so I take inputs from this, to elements of a set y, so these are the outputs. Okay, so what I end up getting is a subset of the Cartesian product of set x crossed with set y. Okay, so think about the Cartesian product of two sets. That's just a bunch of ordered pairs, right? So you've probably seen a function written as a set of ordered pairs before. Okay, where the first value in the ordered pair is the x value, and the second value in the ordered pair is the y value. So this is just a set of ordered pairs. Okay, and what makes it actually a function is that there's exactly one y value in the ordered pair for any x. Okay, so if what you can't have. You can't have like 1 maps to 2 and 1 maps to 7 and 1 maps to 13. Like, so you can't have the same x mapping to a bunch of different y's. This is not a function. That's actually called a relation. You probably also have seen that in your life. Okay, and we're going to cover relations in the next chapter. Okay, but so in a function, you can't have the same x value mapping to different y values. It has to map to exactly one unique y value. Okay. And you've probably seen, if you're thinking about, rather than discrete functions like we're talking about, continuous functions, you might think about, oh, well, let's say I had, a parabola, and I wanted to know, okay, is this a function? You're probably familiar with the vertical line test, right? So I would take a vertical line and move it along my function and make sure that if I looked at the graph, it only ever intersected a vertical line once. So what's that doing? It's checking every single x value here and making sure if I go up, I only find one y value that maps with it, or that it maps to, right? So if I have, an ellipse, for an example, okay, and I'd pass a vertical line, okay, here's an x, but it's got these two different values, okay. So if I looked at the ordered pairs, maybe this is like -2, 4 and -2, 8 or something. Well, there's two different, x values that map to the same y value. So that's not a function, right? That's why the vertical line test works, because it's checking if I have multiple y values that are mapping to the same x value. Okay. You can still use the vertical line test, but not all of our functions are going to be written out, okay, where you can just look at the graph. Okay. So we need to know the definition, but still, the vertical line test will still test that to see if you have a function. Okay. So you probably are familiar with the word domain. So the domain is the set of all the possible inputs, or that's where we get the inputs from, right? This we call the domain. Okay. And then the set Y over here is called the target. Okay. Or sometimes it's called the codomain. You might see both of those words depending on what textbook you read. Okay. So you might be thinking to yourself, oh, well, I call that the domain and the range. So there is a domain and range. We're going to go talk about the difference between target and range, okay? But, okay, the set of values over here that these y's are a subset of, like if you put all the y's together and they're a subset of over here, that's the target. Okay. So what is a range? Okay. And there's a subtle difference that we have to understand. So the range, so an element y is in the range if and only if you can actually find an x in the domain that maps to it. Okay. So the idea here is that you might have extra stuff in the target that isn't actually in the range. Okay. We'll look at an example. Okay, so the range has to be a subset of the target, not necessarily equal to the target. So let's say I define a function, okay, and that the domain is all real numbers, and this is always the target. The second thing is always the target. So if I look at the domain and the target, this, f goes, and this tells me where my cross product is coming from. Domain, target. So my domain is real numbers, my target is real numbers. Well, what about the range? Well, the range is only the collection of values that are actually produced by the function. Okay, so if you think about the values, what is the range of this function? Anybody know that after, I might write. Y are real numbers. Like, what does the graph look like? So what is it? And so it's -4 and above, because the graph looks like a parabola that starts down here at -4 and goes up like this, right? So if I'm looking at the legal y values, the smallest possible y value I could get is -4, and then it goes up from there. So in set builder notation, okay, we would say that y is real numbers such that y has to be greater than or equal to -4. Yeah, from calculus you're used to interval notation where you would be like, so this is the same thing as -4 infinity, right? Okay, but this is set builder notation, which your book is going to use, because they like you to practice using sets. Okay. And so one thing that you'll notice here is that the range and the target are not the same. Okay, the range is certainly a subset of the target, but it's not exactly equal to the target. Okay, so that's the subtle difference. So we're just saying, well, we're defining a function where all of the inputs are real numbers, all of the outputs are real numbers, but we don't necessarily get all of the real numbers as outputs. We only get the values that are greater than or equal to -4 as our actual outputs. So that's our range, even though, okay, our target is a much bigger set. So there can be extra things in the target that aren't in the range itself. Okay. So that's what that looks like for, a function as you typically see it written. Sorry, yeah, what? Yes, I can leave it there. I also am recording this. Got it? Okay. You've also probably seen functions where we're talking about smaller domains and smaller targets or smaller ranges drawn with these things called arrow diagrams. Okay, so we can represent a function with an arrow diagram. Now this isn't practical if we are talking about all the real numbers, because you can't list them all out and draw little arrows for them. But if you have small finite domains, then this is a very practical way to visualize and get a handle on what the function is. Okay, so when we draw this over here is going to be our domain. Okay, this big group over here, this is our target. Okay, so our domain is the set A. That includes, all of these elements, A, B, and C. The target is this whole set, the set B. It includes, -1, 0, 1, 2, 3. I'm going to just put them in numerical order. Okay. But the range is the only actual outputs that are produced. Okay, so the range, Okay, if I look at this, well, 3 is one of the outputs. B maps to 2, so 2 is one of the outputs. C maps to 3. Okay, but the only outputs you ever get are 2 and 3. Okay, so our range is just the values 2 and 3. So there's extra values in the target that never actually get mapped to. Okay. So hopefully that, helps clear up the difference between range and target. So I'm still defining a function that maps elements of A to elements of B. Okay. So my target is B, but my range is only the actual set of outputs that I actually produce by the function. Okay. Probably a word that you've seen before, what a well-defined function is. So a function is a well-defined only if every element of the domain maps to an element in the target. So you have to actually provide a mapping for everything in the domain. Now you don't have to cover the whole target, but you have to have a rule for everything in the domain. Okay. So let's look at a couple of examples down here and see if these are well-defined functions. Okay, so down here we've got the domain is all real numbers. We've got the target is real numbers. And let's say I define a function f of x equals 1 over x plus 3. Okay, so this is only a well-defined function if every single number, every single value in my domain would map to a value in the target. Okay, so so just kind of think, all right, so if I put 1 in there, yeah, that's going to map to 1/4. If I put 0 in there, that's going to map to 1/3. Okay, so can I just put every single number, every single real number into this function and get it to map to another real number? Or can you detect a problem? So Ethan, what's the problem? -3 is an issue, right? So if I put -3, -3 is definitely in the domain, what's listed as the domain, but if I put -3 into this function and I try to do 1 divided by 0, that doesn't give me a real number, it's undefined. Okay, so this is not well defined. Because -3, which is in the domain, does not map to a real number. Okay. So if we wanted to have a well-defined function, we would have to change the domain to be all real numbers except for -3. Right? So if I wanted to write a well-defined function, I would have to change my domain and not make it be all real numbers. Okay. Okay, let's look at the next one. Again, my domain is all real numbers. My target is all real numbers. Okay. Does every single real number map to a real number? So no matter what x value I put in, will I get a real number? Yeah, this one is fine. This one is well defined. Okay. Because every x that's a real number maps to a real number. Okay. Now, if we were trying to take square roots of negative numbers, that could give us problems. If we have, some kind of rational expressions, we have to be concerned about denominators. We're never dividing by zeros. But every single polynomial function is well defined. Never gives us problems. Okay. All right. The next concept is equal functions. So two functions, f and g, are equal if and only if, first, they have the same domain and target, and second, no matter what input you take, they always produce the same output. So if you take f of x, it produces an output. You take g of x, it produces output, and they have to be exactly the same. Okay. So as long as they always produce the same outputs for every input, they are considered to be equal functions. Okay. And we would just use the notation that f equals g. And you don't have to kind of put the f of x equals g of x. You could just call the functions f and g. So let's look at a couple of examples, and I'm sorry, this third one is just a copy of this first one, and I didn't catch that, so I don't know. Maybe I was thinking I was going to give you a different one, but I'm not sure what it was, so just throw that out. It's exactly identical to the top one. Okay, so the top one, okay, the first thing we have to check is, do F and G have the same domain and target? So here's F and G. So I look, domain, same. Target, same. All right, so they do have the same domain and target. Okay, so that one's good. And next, we have to check for every value of x, is f of x going to equal g of x? So if I go to this function and I do f of x, I'm going to get x squared. Okay, if I go to this function and I do f of x, I'm going to get the absolute value of x and square that. And now the question is, are those always equal? Okay, so is x squared always going to be exactly the same as the absolute value of x squared? Yeah, these are always equal. Okay, this is true for all real numbers. Okay, so since they have the same domain and target, and f of x always equals g of x, we would say that f equals g. These are equal functions. Okay. So let's look at this one. So the first thing to check is, do they have the same domain and target? Okay, domain, real numbers. Domain, real numbers. Look at the targets, real numbers. This one is positive real numbers. Okay, they don't have the same target. Okay. Okay, so at this point, you can say, all right, they're not the same. The functions aren't the same. So be really careful about that, because if you were to look at this, if you expand this, you would get x squared minus 4x plus 4 plus 3. That's x squared minus 4x plus 7. You might think, oh, these are exactly the same thing. And you'd be tempted to think that these are actually equal functions. But because their targets aren't the same, okay, we say that they're not the same function. Even though if you expanded them, they look like they are. So don't be fooled. Make sure that you check the domains and targets. Okay. So these are not equal functions, simply because the targets aren't the same. Okay. Then this one on the bottom, okay, we've got two functions. So x, the domain has the number 0, 1, 2, and 4. Okay. And f notice that the domain and the target are from the same sets. That's fine. Just like you could go from real numbers to real numbers, you can go from one set to another set. And f of x is defined as, you take the input, subtract 2 from it, square it, that produces output. Okay. And then the g function is defined using this arrow diagram down here. Okay. So first of all, we want to check the targets. Okay, well, they both have, or the domains and targets. So they both have a domain of x. They both have a target. Okay, so if I look at these, so the domain and the target are the same. Okay, so that part of it checks out. And so now you need to see if every value of f of x equals every value of g of x. Now this is a small domain, so we could just go ahead and check them. So let's go through here, and let's go through every value and say, okay, well, 0 is in the domain, so if I do, what is f of 0? Well, f of 0, I would just take the input 0, subtract 2 from it, square it, that gives me 4. What about f of 1? Well, I would just pick 1, subtract 2, square it, that gives me 1. What about f of 2? I would take 2, subtract 2, square it, that gives me 0. And what about f of 4? I would take 4, subtract 2, square it, that gives me 4. Okay. Those are the only possible inputs, and these are the outputs that are produced by those inputs. So that's the f function, and down here I've got the g function. Okay, here we've got all the possible all the possible domain values, 0, 1, 2, and 4. Okay, so let's look at what g of 0, g of 1, g of 2, and g of 4 are. Okay, So on this one, we just kind of follow the lines to see the association. So if I have an input of 0, I follow the arrow. Well, that gives me an output of 4. So this one is 4. If I have an input of 1, I'll just follow the arrow. That gives me an output of 1. If I have an input of 2, follow the arrow. That gives me 0. An input of 4, follow the arrow. That gives me 4. Okay. And sure enough, every f of x matches the g of x. So f of x equals g of x for all values of x in the domain. So we would say that these are equal functions. That's good. All right. So there are some interesting functions that you've probably come across. The floor and ceiling functions, also known as the greatest integer and least integer functions. So we will look at those, and hopefully this is review and you've seen these before. These are also called step functions. So you've probably studied these at some point in your mathematical past. So the floor function maps a real number to the nearest integer, okay, in the downward direction, we say. So the floor function, this is supposed to be a double struct R, so it maps real numbers. So the real numbers are the domain, and the target is integer. So the output is going to be an integer. Okay. And the way that I take any real number, and the way that I map it to an integer is I'm going to choose the largest integer, okay, such that y is less than or equal to that integer. Okay. So I like to kind of draw myself a little number line here. So like, let's say here's 0, here's 1, 2, 3, 4, 5, 6, 7. Okay. So if I go to 3/4, and I go on my little number line over here, okay, well 3/4 is right here between 0 and 1, about right there. Okay. So the floor function says, all right, I'm going to map 3/4 to an integer. And the way that I'm going to map it to an integer is I'm going to go down to the biggest integer that is less than or equal to my current position. So if I'm here at 3/4 and I go down to the next integer, I just follow along. There's the next integer that I get to in the downward direction. Okay, so this one is going to map to 0. If I go to 4/3, well, that's like 1 1/3, right? So 1 1/3 is about right here. Okay, so the floor function goes down to the next integer. So I just go down until I find the next integer, and I stop. That's at 1. So notice the little the things on the bottom that tells you I go down until I get there. So this one is 1. All right, so if I'm at 6.99, I'm almost up here at 7. But the floor function says I got to go down to the first integer that I reach. So I got to go down until I find an integer. That's 6. Okay. So it's very different than rounding, right? I'm not rounding. The 6.99 would clearly round to 7. Okay, it's going down to the next integer. Okay, this doesn't like throw computer scientists for a loop, because this, like, you know, like often like when you cast things, it does it this way in a lot of programming languages, anyways. Okay. The one that gets a little bit tricky is this one, negative 3.05. Okay. So a lot of people are tempted to say that the floor of that should be negative 3. But if you look at the number line, okay, negative 3.05 is right here, right? It's like right here. And if I go down to the next integer, I'm going to go down this direction, and negative 4 is the first integer that I come to. It's the largest integer that's less than or equal to that. So this one is negative 4. It is not negative 3. The negative ones are a little bit tricky. So if you have trouble wrapping your head around that, just draw yourself a little number line and it's easy. Okay. And then if you already have an integer like 2, here I'm at 2, and notice part of the definition is equal. If you're already at an equal, or already at an integer, I don't have to go anywhere to get to an integer. Okay, so I'm already at an integer, Okay, so the floor of any integer is just that integer. So the floor of 2 is still 2. So don't go down to 1. I'm already at an integer. Just stay there. So there is an equal as part of the definition. So that is the floor function. And very similar to that, there is the ceiling function. Same kind of idea, but instead of going down to the next integer, I go up. So that's why we have these little, you can see on the ceiling function, the little, where the little lines there are, give you an idea, okay, I'm going to go up to the next integer. All right, so once again, a number line can be helpful. Let's see, I want to put 4 and 3 on here. Okay, that's probably good. Okay, so if I'm thinking about negative 17 thirds, 17 thirds, that's 5 and 2/3, right? So if we're talking about negative 5 and 2/3, I'm down here. Okay. So if I'm doing the ceiling, I'm going to go up to the next integer. So this time I'm going to go up until I find an integer. Negative 5 is going to be that one. If I'm at 3.02, well, here's 3.02. It's just right after 3. Okay, so the ceiling says I'm going to go up until I find an integer. So I go up, and the first integer I find is 4. So this one is 4. If I'm at negative 4, already at an integer. Okay, I don't have to go anywhere to get to an integer. I just stay where I am. So this one is negative 4. Are you guys familiar with floors and ceilings? You've seen these before? Yes. Okay. We have a game that we play in my family. I call it the dice game. And we always play it at Mama Rosa's when we wait for pizza there. So we take dice and we roll them when we get 3 numbers. And then you try to take those, like if you, let's say you roll a 6 and a 3 and a 2. Then you have to use the 6 and the 3 and the 2 exactly once in some kind of mathematical equation to come up with every number from 0 to 10. Okay, and sometimes it's really hard. So I had to teach my children about floors and ceilings really when they were really young, because sometimes if you use floors and ceilings, you can get all your equations to work out. So my kids are pretty good at floors and ceilings, and they learned them when they were like, I don't know, in 2nd grade or something like that. So I don't know if you have a weird family like that, and you've been doing floors and ceilings since you were a little kid at Mama Rosa's while waiting for pizza, but that's what we do. Okay. But at least you've probably seen them in high school, and definitely probably in calculus. Okay, so here is an application where these kinds of things might show up. So let's say you have that customers are charged by the hour to park in a parking lot. You've all been there. Okay, so any portion of an hour is charged for the entire hour, of course. So you park there for 2 minutes just to run in and get, and then they charge you for an hour. Like, why? But that's what they do. Okay, so if the hourly rate is $6, then we would like to write a function of f of x for the cost of parking, where x is the time in hours. Okay. So here's your function, okay? And you know, when you park, you don't park for whole numbers of hours, right? You might park for, 1/20th of an hour. You parked like 3 minutes, okay? But of course, you parked 1/20th of an hour, but they're still going to charge you for a full hour, okay? So there is going to be $6, okay, times. And then they don't just, take your value x of how long you parked. What are they doing with it? They're taking it and they are rounding it up to the nearest full hour, right? So they're going to do the ceiling. So if I park for 3 minutes, which is 1/20th of an hour, they're going to round it up to the next integer, 1 hour, and they're going to charge me $6. If I park for 59 minutes, 59/60ths of an hour, they're going to round that up to 1, and they're going to charge me $6. If I park for 20 minutes, that's 1/3 of an hour. That 1/3 gets rounded up to a full hour. Oh, I forgot to. Oh, no, I did. I plugged it in. But it's running low. I have no juice. Is this one not connected either? Oh, that one's connected. Okay. So you can imagine, okay, even if you're writing a computer program or something, you know, that's how you would program the amount that you have to charge the person for their parking fee. Okay. On the other hand, maybe you have a cell phone company and they charge customers for a phone call. There's a 50-cent connection fee plus 10 cents for each full minute of the call. Now, so they're nice. So if you only talk for 59 seconds, all they charge you is the 50-cent connection fee, and they don't charge you for the extra minute. So they only charge you for full minutes. Okay. So they're going to round down the nearest, the length of your call to the nearest whole minute. Okay, so this one, if I would have g of x, okay, I always get the 50-cent connection fee, okay, but I only pay for extra minutes, okay, for full minutes. So they would take the amount of time that I talk in minutes, and let's say I talked for 2.4 minutes. Okay, they would only charge me for the 2 full minutes. So they would take this and round this down to the whole number of minutes and then charge me 10 cents for each of those. Okay. So both of those are examples of where, you know, ceilings and floors would show up perhaps in practical situations. So properties of functions, and this might be all we get through, but this is that's about half of this chapter, which is what I was hoping for. Okay, so one-to-one functions, you've probably seen this as well. Okay, so a function is one-to-one or injective if you look at 2 different values of the domain, okay, and they will always map to 2 different values in the range. Okay, or in the target. Okay, so the function always maps different elements in the domain to different elements in the target. Okay, so you probably have seen a test for this, the horizontal line test. You know, the vertical line test tells you if it's a function and make sure, every x value maps to a unique y value. It doesn't go to more than 1. But if you think about, you know, let's go back to our parabola example. This one is a function because every x value maps to one y value. But it's not one-to-one. Okay, so if I look, for example, at, you know, an x value here, and I look at another x value over here, okay, so this one and this one actually map to the same value. So this f of x1 and this f of x2 are exactly the same. Okay, so that's what the horizontal line test is testing, right? The horizontal line test is seeing, okay, do you have at least two different x values that map to the same y value? If so, then it's not one-to-one. Okay, so the horizontal line test is probably the one that you've seen in your lifetime to test and see if a function is one-to-one. So if it passes the horizontal line test, I know that every x maps to only one y, and that's not duplicated by another x. Okay, so you've probably seen it with graphs of functions, but let's think about how that would look in these arrow diagrams. So we have a few different arrow diagrams here. So here, okay, we have the domain. And this one, notice that a value from the domain maps to 2 different values in the target. Okay, so we know that one's not a function. This is not a function. So in a function, every value of the domain would have to map to only 1, right? So this would be like, 1 maps to 2 and 1 maps to 7. Not allowed. That's not a function. Okay, so if we're looking at arrow diagrams, the way that you can look at it is make sure there's only one path or one arrow. Okay. So there's more than one arrow, okay, out from a domain element. So that's what you want to look for in these arrow diagrams. So this has 2 arrows coming out. Right away you look at that and you say that's not a function. because that's not mapping to a unique value from the target. Okay. I come over here, the first thing I could do is check, is this a function? Well, I could just check, is there only one arrow coming out? Yes, 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 yes. As long as there's only one arrow coming out, I know this is a function. So this one is definitely a function. Okay. Now the question, is it one-to-one? So one-to-one says that I never have two different values that map to the same thing, right? So I'm never going to have this situation where I have two different values, but they're giving me the same output. Over here, if I look, I have this value from the domain and this value from the domain, and they're both giving me the same output. Okay. So it is a function, but it's not one-to-one. Okay. And the way that you can check that, okay, I see that there's more than one arrow coming in to a target value. Okay, so that happens right there. So then if I look at this one, okay, is it a function? One arrow out, one arrow out, one arrow out, one arrow out. Definitely function. Is it one-to-one? One arrow in, one arrow in, one arrow in, one arrow in. Okay, so that's the way that I can check them. So this one is one-to-one. Okay, how about this one? Is it a function? Yep, I see some head shaking. Yes, this one's a function, only one arrow out. Is it one-to-one? No, it's not one-to-one. Okay, because we see this right here where it's got multiple arrows coming in. And this one arrow out, it's a function. One arrow in everywhere, so it is one-to-one. Okay, the next concept we have is an onto function. Okay. So a function is called onto or surjective. So injective is one-to-one. Surjective, that's another word for onto. And that happens when the range and the target are the same thing. Okay, so that's the question there, is onto if the range and the target are actually the same thing. Okay, these are the same, let me just, so this one was not a function. Let me just write these down. These ones are all functions. Okay, this one was not one-to-one. This one was one-to-one. This one was not one-to-one. This one is one-to-one. Okay. And now we want to look at and see if they're onto. Okay, so onto simply means that the target and the range should be equal. Okay, don't have to consider that when it's not even a function. Here are the target and the range the same thing. No, they're not, because I've got this extra thing down here. Okay, so the range is only these values that gets mapped to, but the target is all of these values. So the target and the range aren't the same, so this one is not onto. Okay, this one, same situation, right? We have this extra one down here. This one is not onto. Over here, okay, every single value that's in the target has an arrow coming into it, has something mapping to it. So this one is onto. The target and the range are actually the same thing, so this one is onto. Same thing over here. There's no extras. Every value, okay, in the target has an arrow coming into it. Okay, so the the target and the range are the same thing, so this one is onto. Okay. So notice we have every possible combination. It can be neither one-to-one or onto. It can be both one-to-one onto. It can be one-to-one not onto, or not one-to-one and onto. Okay, so being one of those things does not necessarily imply the other. Every combination is possible. Okay. So you need to test those things separately. Now, it's very convenient when we do have both things that are one-to-one and onto, and we have a special name for those, and those are called bijections, like by-to, right? So there's two important things happening. They are both one-to-one, and they are onto. So that's called a bijection, also sometimes called a one-to-one correspondence. That might be the word that you've seen more frequently. Okay. So often it's very convenient, and most of the functions that we like them to be one-to-one and onto most of the time. So for example, let's say that we were trying to write some kind of function that maps the courses taught during a certain time slot to a classroom. So imagine, here we've got the courses, that's our domain, okay, and here we've got the classrooms, that's our target, and we have some function that maps courses to classrooms, okay, during a particular time slot. So let's say it's, the 3 to 4:15 time slot, okay. So why might we want this function to be a bijection? Okay, so why might we want it to be, let's first think about one-to-one. Okay, is it important for the function to be one-to-one? Yeah, why, Victor?
Because you want to have like a specific classroom for each course, like for the one-to-one like that.
Okay, so what would be the problem if it wasn't one-to-one?
You have like two courses pointing to the same classroom.
Right, so we could have two different classes meeting in the same room at the same time, and that would just be chaos, right? Like we're trying to hold two classes in this classroom, two completely different classes, and two professors talking, and you have to pay attention to one and not the, it would be awful, right? We would hate that. So we do not want two different courses in the same room at the same time. Okay, definitely. So we definitely want a one-to-one function. Okay, and then why would we want it to be onto? Yeah, so we would like all of the classrooms to be used, right? So otherwise, it's a really bad use of our facilities if we have only two classes and then we have hundreds of empty classrooms. That's not an efficient use of our resources. So our goal is to try to have just enough classrooms on campus so that we can kind of keep them full. We don't want to build 100,000 buildings that cost a lot of money and then never use the rooms, right? So, but we also, would like to have classrooms that would accommodate all of our students as well. So there's a fine balance there, but so why onto? Okay, we want our classrooms to be utilized efficiently. Okay, not a bunch of empty classrooms. So I'm sure we don't have an actual bijection. I'm sure there's some empty classrooms, but our goal is to try to get as close to that as possible. And I'm sure there's certain times of the day where we do have a bijection, okay, and other times, like the middle of the day where there's a bunch of classes, probably early morning and later in the evening, we don't have quite the bijection. Okay, but if we have bijections, for a large majority of the time, then we're using our facilities well. Okay. All right. So we can also use these kinds of characteristics of functions, like looking at the domains and the targets and seeing if a function is one-to-one onto, to infer the relative sizes of the domains and the targets. Okay. And this comes up a lot in counting, and I'll show you one cool counting thing, and maybe it will blow your mind if you've never seen it before. We'll see. Okay. So if we have a function, okay, and from the domain to a target, and it's onto, and that's all we know about it, it's onto, then we can say, well, if it's an onto function, then the cardinality of the domain has to be greater than or equal to the cardinality of the target. Okay. So think about it. So if I have a picture here, so here's my domain, here's my target. Okay. Well, because it's onto, every single value of the target is mapped to. There's no extras, right? So I've got things coming in here, and every value is mapped to. There's no extras. Okay. But we didn't say the function was one-to-one. Okay. So it may be that we have things in our domain that are kind of getting doubled up. So I might have this that maps to the same one over there. And I might have another one over here that maps to the same one. So I could have multiple values in my domain that are mapping to the same target value. So I can have multiple domain map to same target. Okay. So what that's going to mean is that the domain is greater than or equal to the target. Sure, if it happened to be like everything only mapped to one, then they could be equal, but there could be multiple ones over here, so the domain is going to could have more than the target. Okay. So if all I know is that that is one-to-one, the domain is greater than or equal to the target. Okay. Let's say that all I know is that it's one-to-one. Okay. I don't know if it's onto. All I know is that it's one-to-one. Okay. So I have the domain, I have the target. Okay. So the domain value here maps to a target. The domain value here maps to a, okay, so they all go to one value. Okay. But, so I know that every domain value maps to a single target value. Okay, there's not multiple ones over here that are mapping because it's one-to-one. Okay. But I don't know it's onto, and so I could have extra stuff down here. So I could have extra target elements that don't get mapped to. Because notice, all I know is it's one-to-one. I don't know it's onto, so I don't know if the domain, or sorry, the target and the range are actually the same thing. So we very well could have that the target and the range aren't the same thing, and there's extra values in the target that aren't in the range. Okay. So if this is the kind of situation, I know that the domain has at least as many as the target, but the target could have extra ones that aren't accounted for as well. Okay. Now, if it's a bijection, then I know it's both of these things. Okay. So this one has to be true. This one also has to be true. The only way for these both to be true at the same time is if the domain and target are equal. Okay. And that's really significant because if I want to show that two sets have the same cardinality, they have the same number of elements, then if I can, all I need to do is define a bijection between them. So if I can define a bijection from one set to another set, I can guarantee that they have the same number of elements. Okay. So this comes up in counting all the time. So have you ever wondered, okay, here's the set of integers. Let's just do the set of positive integers. Okay. So that's the set that contains 1, 2, 3, 4, 5, 6, and on we go. And let's think about the set of positive rational numbers. Let's just start there. Okay. Positive rational numbers. Like this one's a little bit harder to list, but you can imagine like all of these could be written as fractions. So I could write this as 1 over 1, 2 over 2, 3 over 3. Sorry. 2 over 1, 3 over 1, I don't even know how to write fractions, 4 over 1, 5 over 1, 6 over 1, right? So we got all of those. But there's a whole bunch of other rational numbers as well, right? So I could write like 1 over 2, and 2 over 2, 3 over 2, 4 over 2, 5 over 2, 6 over 2. Now some of these reduce to the same things, and so I've repeated some, but it's just convenient for us to see a pattern this way. Okay, so those give me like all the fractions with a denominator of 2, but then I've got all the fractions with a denominator of 3, like 1 over 3, 2 over 3, 3 over 3, 4 over 3, 5 over 3, 6 over 3. I have all the ones with the denominator of 4. I mean, it seems like I've got a whole bunch of these, right? 4 over 4, 5 over 4, 6 over 4, and on they go, and I just can go forever. So, are there more rational numbers than integers? Sure looks like it, doesn't it? I mean, here, I could just match these up. These are the same, and I would just go on and on and on forever, and I would never get down to these ones. But it turns out there's the same number. Actually, there's the same number in this set and in this set. So if I just define a bijection from one set to the other set, I can show there's actually the same number. Okay. So the trick is, how do I get a bijection? Okay. So I can say, all right, well, I'm going to map 1 to this one. Okay, I'm going to start here. Okay. I'm going to map 2 to this one. I'm going to map 3 to this one. I'm going to map 4 to this one. I'm going to map 5 to this one, 6 to this one, 7 to this one, 8 to this one, 9 to this one, 10 to this one, go down, 11, 12, 13, 14, 15, 16, 17. And you get the idea. So if I do a careful mapping, I can cover every possible fraction I could ever write. And now I know, because I've defined a bijection between this set and this set, that the cardinality of the number of positive integers is exactly the same as the number of positive rational numbers. Okay. So it seems like there's more of these, but they're not. They're actually the same. Okay. So I could even go on and say, well, hey, what if you add the negative? Like, what if I say all rational numbers? Let's say I wanted to just look at the integers, the positive integers, so 1, 2, 3, and 4, on and we go. And every single rational number, the positive ones, the negative ones, 0, are those the same? Yeah, those are actually the same as well, okay? So even though there's like an infinite number of negative ones over here that we haven't accounted for over here, it's actually the same number as this set and as this set. I just have to find a bijection that maps. So let's say I could just go 0, and I'll kind of put that in the middle, and I have all these same ones, 1 over 1, 2 over 1, 3 over 1, 4 over 1. You get the idea. All the ones with 2 as a denominator. All the ones with 3 as a denominator. On and on these go forever and ever. Okay, then I've got all the negative ones too. So I've got like negative 1 over 1, negative 2 over 1, negative 3 over 1. And okay, negative, oops, I forgot 2. Okay, and these go on and on forever as well. And these go on and on forever as well. Okay. But if I just find a clever way to do a mapping, I say, okay, well, this is going to be my first one. Okay, and then I'll map 2 to that one, and I'll map 3 to this one. And then I'm going to go over to the other side. I'm going to map 4 there, and then I'll map 5 there, and 6 there, and then I'll go back to this side, 7, and then I'll go to 8, and 9. Oh, I should have gone this way maybe, sorry. That way my arrows will be nice. And I can go this way, and down this way, and down, and then I'll go up this way, and then I'll go over that way, and down, and then I'm going to cover all of them, right? And so, because I can define a bijection between this set and this set, I know that the number of positive integers is also the same as all of the rational numbers. Okay. So, these bijections come up in counting, trying to show which things have the same cardinalities. And it's interesting, all right, and then, okay, if we had time, and we're not going to do this, but the big question is, do we also have the same number of real numbers? What's really crazy is there aren't. There's more real numbers. So there's an infinite number of rational numbers. There's an infinite number of integers. But if you look at the real numbers, there's more than that. You can't define a bijection between the integers and the real numbers. So there's different kinds of infinity. So some infinities are more infinite than others, and it's kind of crazy. So Let that blow your mind if you've never thought about that. It's too bad we can't do that proof today, but we're not going to. I'll just tell you it's true, and you'll be like, whoa. Okay. But if anybody ever tells you they're the same, they're not. Okay. All right. Yeah, that's good. We'll start with this one next time, but you need to do Zybook sections 5.1 to 5.3 before the next class. Okay, it shouldn't be a lot. It's just, I know a lot of this is review of stuff that you've done before. It shouldn't be. 5.1 to 5.3.
No quiz?
No quiz. 5.1 to 5.3.